So thank you. I will switch to English to a little balance the situation for our colleagues from abroad. We are from Global Change Research Institute, and we are not the specialist in the problematics of noise and traffic noise and similar stuff. But for this module in the methodology, we invited Mr. Krivánek from Transport Research Center in Brno, who is the person that was guiding us to not make some obvious mistakes. If I start from the general problematic of noise in the cities, I would mention that it is also in the legislation of European Union. In the basic document is this directive from the year 2002, and based on this document we can identify three pillars or three levels at which the problematic is solved. The basic one that is supporting all other is noise mapping, when basically each state should create some kind of a noise map. The methodologies how to do this are different. For example, Czech Republic adopted the methodology from France, and the responsible institute in Czech Republic is Ministry of Health, who also published this noise map on their portal, and it was one of the inputs into our methodology and the software as well. The other level is the level of the mitigating measures, which should be designed and constructed in the places based on this noise mapping, and here it starts to be also interesting for the people dealing with vegetation, because as the technical measures are usually more effective than the vegetation ones, it was also observed that there is a psychological effect that the people usually accept the higher level of noise or higher level of sounds better if there is a presence of vegetation in the environment. And the last level are so-called quiet areas or silent areas, which should be defined and also maintained and somehow protected at the landscape level, also at the level of individual cities. And if we come to the technical part of the methodology, I sadly start with some physics and characterization of the sound and so on. So basically the sound is a mechanical wave that is propagating through the environment, through the medium, which in our case is air around us. And the wave can be characterized by its wavelength and amplitude, and these together can be combined into an intensity of the sound. And another characteristics are speed and also direction. This is a simplified display of the sound wave in the air. Basically, it is propagating as a localized change of the pressure in the air. These are some basic informations. We usually know that our ears, our receptors have some sensitivity to different frequencies, to certain temporal resolution of the sounds, and that we perceive the sounds as a interference of different waves of different frequencies, which is denoted somewhere here. And that different people of different age have different sensitivity to different frequencies, which can be also interesting with respect to traffic noise, as we will see a little bit later. Here is a definition of so-called sound level, which is basically the loudiness of the sounds, and it is basically a ratio between the actual pressure caused by the sound and the limit of human apparatus to distinguish sounds. Which brings me to what we perceive as a noise. Those are just sounds, but usually they are not periodic, somehow not harmonic, or simply too loud. Here I just demonstrate the spectral domain of the traffic noise. At the left picture you can see a spectrum of road traffic noise, which we can perceive in the streets, compared to the noise caused by the high-speed train, and we can see that the rails are having higher amount of higher frequencies. That this is the link to the sensitivity of people to different frequencies. Here just a small refresher that the studies exploring relations between sounds and vegetation are quite old, let's say. One of the first I found was from the 1946, when US Army studied propagation of shooting in the jungle vegetation. Here is one of the key slides of the presentation, I would say. That is that we distinguish two basic sound sources or noise sources, which is a point source and linear source in case of road traffic noises, and it has an effect on the sound propagation in the air. Basically, from the point source, the waves are spreading in a hemisphere, whereas from the traffic noise from the road, the noise is spreading in the shape of cylinders, and this spreading of the noise is connected with the natural decrease of the sound level, which is here in the red line. This is the theory, and in case of traffic noise, this natural decrease of sound level can be described by this relationship, where we have two distances from the source, which is denoted here, and a coefficient exponent that is telling us the resistance of the environment towards the sound waves. as mentioned here by our colleague, the decrease if we double the distance from the source in a case of traffic noise is about 3 decibels, which means that the actual loudness of the sound is half. The interaction between vegetation and sound or noise has several aspects. It's a rather complex thing. It depends on the dimensions of the trees or branches or the bushes or any kind of object that stands in the way of the sound wave. And as I mentioned, it also depends on the ground, whether it is acoustically hard or soft, whether it absorbs the waves or it reflects the waves, and the canopy density, of course, and crown base height. Here is just a small example of some study which used a real physical model of sound wave propagation and studied the arrangement of the stems in the tree belt that should reduce the traffic noise and also the height of the obstacle. Our methodology has several assumptions from the perspective of the people who are studying the noise. I would say rather simple, but they should be valid. That with the increasing distance from the source, the potential of vegetation to reduce the noise is decreasing. That the vegetation, which is in some belts or in some groups or patches, has a bigger potential for noise reduction, and denser vegetation, of course, has higher potential. And the increasing height of the canopy base is lowering the potential. If I come to the inputs, we needed information about the greenery, which is coming from the passport or from the inventarization. Basically, it's information about position, information about canopy base height, information about crown diameter and the species. Then we also need a road map, noise map, and to calculate the ecosystem service. We also need information about the resident density. This is a rather messy picture, but I will try to explain what it is about. Because it basically tells us the core information how to get to the attenuation which is caused by the vegetation. In the first step, when we have the points denoting the individual trees, we create buffers based on the crown diameters, and we try to identify groups of the vegetation based on this connectivity of the crowns. Then we calculate distance of these individual groups or individual trees towards the nearest source of noise, nearest road, and we need the distance to the start of the patch or of the group, and then we also need the distance to the more distant part of the group of the polygon to include the width of the vegetation, and of course, as also was mentioned, we calculate the active length along the road. Maybe you can recognize this equation from the previous slide, where I change the exponent simply to x, which is then calculated from the information about leaf area index. In case of the summer period, in case of winter period, we calculate it with the wood area index. And based on the information in the studies we found, and also based on our own measurements in Brno, we came with this kind of a composed relationship between LAI and the value of the X coefficient used in the equation to calculate the attenuation by vegetation. The next step of the calculus is that we calculate two cases. One is with the vegetation, and the other one is without the vegetation. That means that we change the coefficient x to 1, and that gives us the effect of the presence of the vegetation in that place. Then we can calculate effect of the whole the information we get from this equation is a kind of information on the transect, or that is denoted here. At its information without the other dimension. So to calculate the effect of the whole object, we use the active length along the road, and also information about the density and volume of the crowns, which then can be used to recalculate the ecosystem service back to the individual trees. The calculation of the ecosystem service, meaning the monetization of the ecosystem function, is based on a European handbook on the external cost of transport, which also includes this effect of noise, traffic noise. And yeah, that's basically this information in the table and in the graph. And that's basically it. So thank you for your attention. If there are some questions, I will be happy to answer them.